We're going to wrap up boundary layers and external flows early on. We will start with external flows. For Monday's quiz, we're going to see everything up to what we see at the end of the day today, that I believe is going to be entry length. I'll confirm that towards the end of the class. The handouts for this unit on boundary layers and external flows is already uploaded, and for the internal flows are also uploaded too. So let's see where we left on Wednesday. Okay. So if we talk about briefly these units on external flows, internal flows, and natural convection, all three are the whole point of these units is to calculate the convection coefficient H. That's all we're doing. H goes inside other calculations like we have done earlier in the year, like for lumped capacitance or as a boundary condition in a semi-infinite solid. So many things. So all we're doing here is to calculate H. Where does H come from? What number we give to it? We already knew some ballpark values for gases, for water, for natural convection, for forced convection, but now we're calculating it. And we said that the convection coefficient was given by the conduction through a thermal boundary layer. So our whole, and in that case, we knew how to calculate it. You did it for quiz 2, and you did it right. So the challenge now is to say, given that if I'm given a boundary layer, I can calculate H, the convection coefficient. So what is the thickness of that boundary layer? That's all we are doing these days. And so we said, okay, in the case of molten metals, we can calculate it, assuming that the molten metal that is flowing behaves like a semi-infinite solid, because there is a lot of heat transfer, because it's very conductive, but it's not so viscous. And then we said, okay, but molten metals are very fine, thank you very much. I work with water or oil or air, none of which is a molten metal with a very small Prandtl number. So we said, okay, we need to go back and remember the viscous boundary layer from fluid mechanics first. And we said, okay, the viscous boundary layer in fluid flow looked very much like the thermal boundary layer, but the coefficient was not exactly the same. And it's because now the problem is so much more difficult. And poor Blasius, the PhD student of Prandtl, he solved all those couple partial differential equations, and all we care about is that he got a number 3 here instead of a 1.77. And so having this we can calculate the thickness of the viscous boundary layer, and then we can relate the thickness of this viscous boundary layer to the thickness of the thermal boundary layer. And what did we see? We see that for the case of molten metals, that is so uncommon, but it's the first one we analyzed, the ratio between the thermal boundary layer and the viscous boundary layer was proportional to a Prandtl to the -1/2. And we see this -1/2 coming every time we have correlations for molten metals. But for the case of oil, water, and air, we needed to account for the much thinner thermal boundary layer that has much lower velocities because it's closer to the surface, that is where the fluid is flowing slowly. And when we did that, we came to the conclusion that the ratio between these two boundary layers was proportional to a Prandtl to the 1/3. And we are going to see Prandtl to 1/3 all over the place. We also saw that heat transfer, a convective, the convection coefficient is tabulated in the form of Nusselt, depending on Reynolds and Prandtl. And we are going to see this type of expressions all over this unit in this week, next week, and the week after, in which we say Nusselt, right? That is hk over x. So here, really, what we care is about h, is a coefficient. In this case, is 1/3, but doesn't matter. It's a coefficient times Reynolds to the something, typically Reynolds to the 1/2 in laminar flows, and Prandtl to the 1/3 for the case of air, water, and oil. In the case of molten metals, typically this is Prandtl to the 1/2. And in the case of turbulent boundary layers, this tends to be, instead of being a 1/2, 0.5, is a 4/5, 0.8. And we discussed that the boundary layer always starts as laminar, and then it triggers, when it's long enough, it transitions into a turbulent boundary layer, and we would know the transition based on a critical Reynolds number. That, for the case of a flat plate, is 5 times 10 to the 5. But for a cylinder, we didn't even care about that because we have correlations that also needed to account for a wake. But for many other things, we are, for example, fluid inside a pipe, we're going to have a critical Reynolds number that is specific for that geometry. And we saw how, in the case of a turbulent boundary layer, we would have that a boundary layer that suddenly increases in thickness. The boundary layer suddenly increases in thickness, and the Nusselt number that used to decrease with the increase in thickness of the boundary layer, all of a sudden also increases, because not only we have a thicker boundary layer, but we have an enhanced transport process because of the advection that is induced by the turbulence, right? And this turbulence actually makes a thicker boundary layer be so much more conductive that it also has a higher convection coefficient or higher Nusselt number, right? And we see this expression with Prandtl to the Reynolds to the 4/5, that is the 0.8. So when we talked about external flows, we talked about flow around the cylinder, and what we saw is that the standard correlations around a cylinder are things like Nusselt, D, right, meaning that the characteristic length is the diameter, is hd over k, fine, we're going to solve h from there, and has expressions of this type. C, that is a constant, times Reynolds to an exponent, and Prandtl to the other exponent. Look, for air, water, and oil, this is 1/3, and they just put it there. In the sphere, in the cylinder, what we saw is that it's slowly transitioning from laminar, and it always has a wake, right? Even at low Reynolds number. So as we increase the flow, we slowly, the Reynolds number, we slowly transition from something that is mostly laminar to something that is mostly turbulent. And this M factor here indicates that, because at low Reynolds numbers, M is more or less 1/2, and at high Reynolds number is more or less 1/2. That is very comparable to the exponent of Reynolds in a flat plate in laminar flow. But when the cylinder is at high Reynolds number, which is very turbulent, the exponent is more or less 0.8, the exponent of Reynolds, this M exponent here, which is comparable to the 0.8 for heat transfer correlations for a flat plate in turbulent conditions. Right? Here we see one for 7.44, okay, right? And okay, so There are correlations also for the case, often for a single geometry, you might have many correlations. And it's many people doing the same research and reporting results that are more or less the same. If there is a difference, typically it's because their experiments aiming to do the same thing were slightly different. So we see this formula here that is also convenient because it's so simple, and we use this table. But this but if this other formula that is more complex accounts for the fact that if we have a fluid that is very has very temperature dependent properties, for example, oil has a very very dependent on temperature, its viscosity. I change temperature a little bit and viscosity changes a lot. And the Prandtl number, right, because it's Nusselt over viscosity, Prandtl number is the kinematic viscosity divided thermal diffusivity, is going to change a lot. Similarly, the Reynolds number that depends on the kinematic viscosity is going to change a lot. So what they have done, they say, okay, you calculate everything at the temperature of the fluid far from the surface, right? That is this T infinity. And this very strong gradient in temperature at the thermal boundary layer, which is also a strong gradient in properties. We're going to account with this ratio of Prandtl at the flow temperature divided Prandtl at the surface to the 1/4. Although you see this 1/4 that is so elegant, it's not true. That comes from an empirical correlation. This doesn't come from any fancy derivation. And there are other formulas that are even more complex that are in the book, right? Unless you have to, I suggest you use the simpler formulas. As simple as possible, but not simpler. Simpler than possible means you're missing the boat. But in this case, let's if we do not have the temperature dependent properties of the fluid, we would be using this formula. We did discuss a methodology for solving problems of external flow, and we're going to see that internal flow and natural convection are very similar. So we have 4 steps that I'm going to show with an example, but I'll mention the 4 steps first. Step number 1 is to get the right formula for the geometry we're talking about. This is obvious because if we have a cylinder, we're going to use this formula for the cylinder and not that for a flat plate. And in our formula sheet that I just uploaded, optional for you, you have this long list of everything about geometry of a flat plate or a cylinder or a sphere or falling drop or packed tube bank or packed bed of spheres. So that's number 1 step. You look your formula and you say, what do I want? Do I want the Nusselt number? Do I want the thickness of the boundary layer? Do I want, here we have even some drag coefficients. I don't care about those. We just transcribe what was in the book. But do I want a local value of Nusselt or do I want an average value of Nusselt? Right? We have to know that, right? And that would be the statement of the problem, or in a job in real life, you would know which one you need. So that's step number 1. Let's get the right formula for the geometry. Number 2 is assess Reynolds and Prandtl and other factors that are relevant. So let's go back to our formula sheet. And let's consider a cylinder, for example. Let's see this formula here. And it says Nusselt average, which is a very reasonable thing to ask, has this for a cylinder, has this formula. What do I need to calculate it? I need Reynolds and I need Prandtl. Let's say we're talking about water and water has a Prandtl number of 7. That would be given to you. Okay, I got Prandtl already. Reynolds, well, for Reynolds, I need to calculate it. And it says Reynolds D of diameter. Okay, I would use the Reynolds number using the diameter as a characteristic value. Once I get Reynolds and Prandtl, I need to make sure they fit within this range of validity of the correlations. Many of these things, many of these correlations were made empirically. So they say, in this range, I give you this formula that is going to work well. Outside this range, you're on your own. So if you're going to use these formulas, you can only be happy with what you're doing if it is within the range, for example, indicated here, this range for Reynolds and this range for Prandtl. If you're outside, you might be still use it, but you know that the farther you go, the farther away you are from the range of validity, the thinner and thinner is the ice on which you're skating, right? But it's an informed decision, right? Check it out. This one has Prandtl to the 1/3. And what does it say? That Prandtl should be bigger than 0.7. Let me show you. I believe we're going to find an equation for molten metals. Let me see if I have it because the book has it. Okay. This equation here is the Peclet number is same as, you know the formula for the Peclet number. You can rewrite it as Reynolds times Prandtl, and both to the 1/2. This is for molten metals. And here you get to see that it says for Prandtl less than 0.05. Okay, so the number 2 step was calculate Reynolds, Prandtl, or whatever we need, make sure we're in the right range. Step number 3, we calculate Nusselt number. So step number 3 is to some extent trivial. We plug in Reynolds, we plug in Prandtl. Oh, we need to know what M is to calculate it, right? And we need to know what C is, right? Here it says table 7.1. And here it gives us what the C value is and what the M value is. And we put it, and we calculate Nusselt. Now we have Nusselt. And what does Nusselt tell us? Nusselt itself tells us very little, but we can unpack it, right? Using the expression for Nusselt, that is HL/K. So we solve for H. And in step number 4, after we have, and in step number 4, after we have calculated Nusselt, we calculate H. And then we can start applying H to whatever other problem we cared about. So you realize we are spending 3 weeks on a sub problem, that is the calculation of H. Before, I used to say, oh, it can be 10 watts per meter square Kelvin or 1000 watts per meter square Kelvin. And I hope you believed me and took me seriously, but I made it up, right? Now you can say, aha, is it true? And you're going to see that what the values I gave you, yeah, are quite good, but they're not exact. And they're not exact by plus minus half an order of magnitude. But with this, you can calculate it very well. So let's look at an example in concrete. Let's look at this the way I would do it in an exam. So let's calculate average H for a cylinder of 20 millimeters in diameter, immersed on a cross flow of water that is at 1 meter per second. This is a problem from a former exam, a previous exam. This is the type of thing you're gonna see on Monday in the quiz. So how do we go about it? Well, we're gonna use our 4 steps: identifying the right formula, calculating Reynolds, Prandtl, and whatever it is, calculating Nusselt, and solving for unpacking Nusselt to solve for the convection coefficient that is the equation. But let's pay attention. Look, here it says cylinder. That's important. We know it's a cylinder, not a flat plate, not a sphere. Great. Here it says average H, right? Is average convection coefficient. They are not asking us about local. That matters. If for a plate, we talk so much about local convection coefficient, which we might forget that actually what we use the most in practice is the average, not the local. And here are the 4 steps, the way I wrote them in the answer key. I'm not going to get this right up from you, but this is the right up you would have at home to plug a number. So 1, you select a formula for is a cylinder, is average Nusselt. So what do we have? You can go to the book, you can use this formula sheet, and you can, which is uploaded under, I think I called it useful material or useful concepts. Useful concepts is in the list of topics. And we would see, okay, flat plate. No, I don't care about those. Cylinders. I have 3 things for cylinders. 3. One of those is for temperature dependent properties. So I'm going to tell you if you should account for temperature dependent properties or not. I didn't say anything here, so I'm going to take the easier one and say, let's forget about temperature dependent properties. If I wanted to account for temperature dependent properties, I go to the book, and the book gives me the temperature dependent properties of water. No problem. But since I didn't ask for that, I would do the easy one. Okay, good. So the formula is, I'm not going to use this. I have another one. This other formula down here is a formula that is not for temperature dependent properties, but this formula 7.46 actually is an updated version of this one on top. If I don't ask you for the exam, you pick the easiest one, but not easier than it should be, right? This is good. If you are at work and you have time to calculate something a little bit better, I would use this other formula that is a little bit more complicated. The reason is it doesn't have any, this formula here doesn't have any new physics. This formula down here and this other above are essentially, they are exactly for the same purpose, for calculating average heat transfer coefficient in a cylinder in cross flow with without accounting for temperature dependent properties. The reason they're different is that this on top is an older formula, and this is a newer formula that also accounts for newer experiments. This one here is better than this one on top. Now, let's say this one, the long formula is better than the shorter formula. We have to acknowledge that these formulas are not mathematical, they don't have mathematical exactitude, they have physical exactitude. They have measured these things. But as you know, reality is so much more complex than what you can capture in a little formula. So there are many things that here are not accounted for, right? And would have an effect in reality. For example, roughness of the cylinder. If we have an external flow on a cylinder, and I discussed this when we talked about golf balls. If we were to have this cylinder as part of a heat exchanger, and there is fouling on the outside of this cylinder, a little bit of fouling may trip the boundary layer from laminar to turbulent, and actually the heat transfer coefficient might be enhanced with a little bit of fouling. Isn't that crazy? It's counterintuitive. When you start having more and more fouling, you create a full layer that becomes an insulating layer, and it's bad. Those things, those subtleties are not accounted in these formulas here. We could if we wanted to go deeper and deeper and deeper. So let's not believe that these formulas are given by God. No, they're given by people who measure things many times, and 1 or 2 PhDs after, we get to plug and chug and be annoyed at this little formula, forgetting that before that formula, somebody needed to spend 4 years of experiments. All right, that was step number 1. Step number 2 was assess Reynolds and Prandtl. So for water, Prandtl was 7. For the Reynolds, U infinity d over nu, we calculated, and we get this value for Reynolds, almost 2 times 10 to the 4, right? To calculate nu, we can do it in many ways. It's tabulated. I'm going to give it to you. Or you should remember that Prandtl is nu over alpha. In this case, we solved for nu, saying is alpha for Prandtl, and we use values that are kind of easy to remember, not necessarily exact, but easy to remember. So now we have Reynolds and Prandtl, and let's go to our table again. If I have Reynolds and Prandtl, it tells me Reynolds was 20,000 and Prandtl was Reynolds was 20,000 and Prandtl was 7. So let's go. Easy formula. Let's go to table 7.1. So 20,000. We fell somewhere on this line here, right? Between 4,000 and 40,000. So C is 1.93. You see, that's what we picked here. And M is 0.618. M0.618. That is kind of in between the value for laminar and turbulent. Then I calculate nu using the formula straight, right? I plug in the C, that is 0.193. Let's see the formula again. The formula here is C times Reynolds to the M times Prandtl to the N. And C is 1.93 times Reynolds to the M is Prandtl, Reynolds. Here you have Reynolds to the M times Prandtl, this number 7, to the 1/3, as we typically expect in our problems. And we get this Nusselt, 163. Number one thing to think, is a number much bigger than 1, as it should be, because the Nusselt number was characteristic length divided thickness of the boundary layer. And the boundary layer had to be very thin, so we're dividing by a very small value, and we should end up having a big number in the end. 163 is reasonable. What would be the average thickness of the boundary layer? Well, easy. I know that the convection, the thickness of the boundary layer was given by the thermal conductivity of water divided the H value. Is something you also did in quiz 2. So we have this estimate, and the cylinder was 20 millimeters, and the thickness of the boundary layer was 0.12 millimeters. This is thin, it's okay. All right, I got the Nusselt number, and from there I calculate the H number, right? I solved nu is H d over K, so I can solve for H, and gives me 4,890 watts per meter square Kelvin. Before, I would have said, okay, I ballpark this at 1,000 without knowing anything. Now we do it properly. We're off by almost a factor of 5. Of course, I never like to be off. But the number of 1,000, I totally made up. This number, you can stand for on this number. This number, you can design a heat exchanger on, right? And in the end, it's this easy, following these 4 steps. And this is what we're going to be doing for pretty much all convection problems. This is what you will be doing on Monday, among other things. There are similar correlations for a sphere. Look, what do we see? Reynolds to the 1/2, same as in the plate. Prandtl to the 1/3, same as the plate. And nobody's telling me anything on this slide, but I know This is not for molten metals, and it is for water, oil, and air, right? And we have a coefficient. So this is a very simple formula. Of course, people got excited, and they can always like torture a poor PhD student into doing something more complex. I don't even know if there was a point, but hey, if you want something more difficult, you got it. And there is even another formula in the book for falling droplets. The one thing that I think is cool about this formula is that we have this and a 2 in front. And this 2 is so cool. Imagine the fluid stops moving. If the fluid stops moving, then we have no advection, because advection is transport of heat by motion. So if the fluid stops moving, we have no advection. If we have no advection, therefore we have no convection, because convection is the simultaneous effect of conduction and advection. What are we left with? With only conduction. Becomes a conduction problem. You know what is cool? Remember when we saw these shape factors and these dimensionless heat transfer coefficients? Okay, this number 2 is the exact result for a sphere in conduction. So this formula is cool. It says if you have no advection, you have conduction, and this is exact. If you have lots of advection, then you have convection, and you have this formula that would be a lot bigger than 2, right? Nusselt typically is 100, 1000. And in this case, would be never less than 2, because it becomes a conduction problem. Isn't that cool? I think it's awesome. And the research we're doing in our lab is based on the pioneering research that did this type of heat transfer. And you can do an even better estimate for intermediate regimes using the type of formulas we see elsewhere, but based on this number 2 here and this other value here. Also, something else that is interesting for the case of cylinders, when you have no convection, when you have no advection, right, at zero fluid velocity, actually there is no solution for the solution goes to infinity. So, but the case of infinity is so extreme that all the correlations say in practice you never get to that extreme, and they give you something that is empirical. If you look at this very complex formula here, the one it has a 0.3 here. This 0.3 here does not come from deep theoretical analysis. This 0.3 is just empirical, because if you do the theoretical analysis, the equations diverge. But for the sphere, they don't diverge. And this 2 is exact. You don't need to know this for the exam. I just thought it's cool and I wanted to share it with you. In our own research in welding, we have similar problems about cylinders and spheres. And we learned this the hard way. And only then I went back to the heat transfer book and I said, aha, somebody was cheating here. Okay, good with the sphere. I want to start with, internal flows. As I switch slides, if there is any question that comes up, I'm looking at the chat. Okay.